Good evening, dear President, President-elect, past presidents, Professor Udaya Annakage, our speaker today, Engineer Kosala Ambradeniya, Chairman, Electrical, Electronics and Telecommunication Engineering Sectional Committee, Council members, members of IESL, IESL staff members and invitees. You all are welcome to Professor R.H. Paul Memorial Orations and prestigious calendar. Let me cordially invite following dignitaries to light the traditional oil lamp electronically. Engineer Arjuna Manamperi, President IESL, Engineer Dr. Kamal Laksiri, President-elect. Past presidents, Engineer Chula Di Silva, Engineer A. Ayutthaya, Professor Udaya Annakage, speaker today, Ms. Sonia Kaspers, Professor R.H. Paul, Engineer Kosala Ambradeniya, Electrical, Electronic and Communication Engineering Section Committee Chairman, and Engineer Neela Pesekara, Chief Executive. Thank you very much. Now it is a time for us to pay our profound gratitude to late Professor R.H. Paul. In order to accomplish this, I respectfully invite our President, Engineer Arjuna Manamperi, to garland the photograph of late Engineer Professor R.H. Paul electronically. Thank you, sir. Now let's watch a short video created by the Electrical, Electronic and Telecommunication Engineering Sectional Committee members.
Professor R.H. Paul is known as the father of electrical engineering education in Sri Lanka because of his prominent involvement in the country's development of engineering education. He was born on February 9, 1904 and was an exceptionally gifted student. He obtained his Bachelor of Science General degree from University of London with first-class honours through the University College Colombo at the age of 20, which proves his excellency. In 1928, his name was written in history as the very first Sri Lankan who joined the University of Cambridge and obtained the Mechanical Sciences Tripos with first-class honours. However, with the ambition of serving our country further, he joined the Ceylon Technical College Colombo as a lecturer, which was the only institution offered courses in engineering in the country at that time. In 1942, with the recognition gained by the University of London, the Ceylon Technical College was known as an institution which prepares students for its prestigious Bachelor of Science Engineering external degree programs. In 1950, University of Ceylon established its very own Faculty of Engineering, which initiated the very first step of engineering education, which is present now, and Professor Paul was one of the founder members. As well as he was the first professor for electrical engineering until his retirement in 1968. His encouragement and efforts helped to elevate the status of the engineering profession in Sri Lanka. After his retirement, Professor Paul was elected President of the Sri Lanka Institution of Engineers in 1968, since his extraordinary abilities were exceptionally higher than any person. Professor Paul dedicated his life to establishing an eminent profession of electrical engineering in Sri Lanka foregoing all golden opportunities to guide his own people in their pursuit of a remarkable career in electrical engineering.
Thank you. It is indeed a very creative and informative video. Thank you very much, EENT Sectional Committee officials. Now, let me invite our President, Engineer Arjuna Manamperi, to give away the introductory speech. Over to you, sir.
Thank you, CEO, Executive Secretary Nila Besekar, Engineer Nila Besekar. Can you hear me well?
Yes, sir, we can hear you well.
Thank you. Good evening. We are about to start Engineer Professor R.H. Paul Memorial Oration organized by the Electrical, Electronics and Telecommunications Engineering Sectional Committee of the Institution of Engineers Sri Lanka to commemorate his life and work on the 118th birthday anniversary, which falls today, 9th of February every year. In this August gathering, albeit online, we are all online today, we have an eminent speaker, Professor Uday Annakage from the Department of Electrical and Computer Engineering at the University of Manitoba. Welcome, sir. Family members of the late engineer Professor R.H. Paul, welcome. Past presidents of the ISL, president-elect, vice presidents, and council members, chairman of the Electrical, Electronics and Telecommunications Engineering Sectional Committee, other distinguished invitees, Executive Secretary of ISL, CEO of ISL, staff members, ladies and gentlemen. A very warm welcome to all of you. A very warm welcome. We are online today, so you might be joining from very different places. So whatever it is, we have very warm welcome from Sri Lanka to all of you for joining. The Institution of Engineers Sri Lanka, the apex body for professional engineers in Sri Lanka, holds memorial lectures in memory of engineering giants who passed away doing a momentous contribution to the engineering field and the development of the country. If not for the memorial lectures organized by the ISL, contributions made by great personalities such as Engineer Professor R.H. Paul will be long gone from the memories of not only the public, but also from young engineers. Before we go any further, I would like to establish the purpose for having these memorial lectures in the minds of our young engineers and even us among ourselves. I was listening to the memorial oration introduction by last session President, Engineer KPIU Dharampala, immediate past president, and he finished his speech by stating that people will be remembered for not what they achieve or what they gain from the society, but what they give back. This was etched in my mind. That's how we finished the speech. I still remember. So our memorial lectures, including this one, is for such people. There was a very good creative video by the sectional committee. So some of this information will be redundant, but nevertheless, one of the first things we can learn from Professor Paul is formal education. He had a passion for electrical engineering, but he nevertheless, he was a gifted person, natural student, but nevertheless, he went through some very serious formal education. At the age of 20, he received a BSc General degree from the University of London with first class honors to the University College, Colombo. He received Kumaraswamy Prize for his exceptional skills in physics and was awarded the Ceylon Government Engineering Scholarship for further studies at the University of Cambridge, United Kingdom, a prestigious university. He was the first Sri Lankan to acquire the mechanical science tripos with first class honors in 1928. And the most important thing is he returned back to his motherland in 1930. he returns back. He gets his education, he returns back. He wants to serve the motherland, Sri Lanka. Then he picked his favorite field, engineering education. In 1933, he joined the Ceylon Technical College, Colombo, the only institution for engineering education in the country at that time, as a lecturer. He was a visionary scholar and a practitioner. Now, mind you, this is 1933. The advances he brought to the college were mere cause for one of the key reasons for the University of London to recognize the college for preparing students for the BSc Engineering external degree from the university, Ceylon Technical College. He was single-handedly created the laboratories, lectures, and etc., so that the University of London could recognize our external degree students for the engineering external degree from Ceylon Technical College. With no surprise, he was appointed as the first professor of electrical engineering of the college later. He held the post of director of the college from 1944 to 1949. Although he worked tirelessly to improve the engineering education in the college by teaching extra hours and developing infrastructure facilities, he still managed to find time to contribute to scientific research by writing many research papers, and in appreciation of one of which he won the overseas premium in 1944. He set another example about his journey, through his journey. He never stopped learning. He was pursuing excellence in his field. As an engineer, he continued to do the research work. He was very serious about his field of work, and he never stopped learning. With the establishment of the Faculty of Engineering of the University of Ceylon in 1950, Professor Paul was selected as the first professor of electrical engineering. This was before the times of University of Ceylon, Peradeniya campus. Also, he was among the founding members of the university. He remained at his position until his retirement in 1968, fully devoting himself to the development of engineering education in Sri Lanka. In fact, if you go to the web page of the University of Peradeniya, today, as we call it, engineering faculty, electrical engineering web page, you will find Professor Hall listed as an emeritus professor, because he was there for a few years, definitely. Considering the enormous services he did to the electrical engineering education in Sri Lanka, there is no misgiving calling engineer Professor R.H. Paul, fondly known as that Professor R.H. Paul, but Robert Hyacinth Paul, the father of electrical engineering in education in Sri Lanka. He richly deserves it. He didn't stop there. He didn't stop there. Look at his journey. Though Professor Paul was renowned as an electrical engineering academic, he was also an effective engineering practitioner. Commission of Broadcasting and Information in 1965 and Advisory Board of Technical Education in 1996 are among the few occasions where the government pursued the expertise of Professor Paul by appointing him as a committee member to set up these things, institution. He was an institution builder as well. But he is very much known for his role in transforming the Department of Electrical into today's Ceylon Electricity Board is also noteworthy. Did he stop there? He was building social institutions, taught electrical engineers, hundreds of them, built a faculty. Did he stop? No, he didn't. Because he became the 1945. He became the general president and served Sri Lanka Association for Advancement of Science. He was a founding member of SLAS, as we know it today. He was the general president in 1945. But his pinnacle of his achievement from the professional side as a professional leader came in 1968, the year that he retired. Our institution, the Institution of Engineers Sri Lanka, selected him as Professor Paul as the president of IESL the premier professional body for engineers, Institution of Engineers, Sri Lanka. Acknowledging and commending his immense contribution to the engineering profession in the country. So here's a man who, when he was very young, he studied very carefully what he wants to learn, continued his research work, became a scholar, came back to his motherland soon after his education from the UK, where everybody used to go there at that time. Didn't waste his time there, came back, contributed to the engineering education heavily, built institutions, even such as Ceylon University Board, and later became the president of ISL. These are the lessons that we can learn from this gentleman. Devoting every second of his life to form an eminent engineer profession in Sri Lanka and to enrich the quality of its rich international standards. Professor Paul passed away on July 3rd, 1978, at the age of 74. The University of Ceylon conferred the degree of Doctor of Science on Professor Paul posthumously at its convocation in 1980 in recognition of his yeoman service. He was born in 1904. At the age of 20, he became an educated man, an engineer. In 1970, he passed away. If you do the mathematics, ladies and gentlemen, his life was all about engineering education, electrical engineering education, electrical engineering, and institution building. I think that's what he did almost all his life. And this is what we learn from such greats. So it's no wonder that he's called the father of electrical engineering in Sri Lanka. Now, to honor him further, today, the sectional committee chairman and the sectional committee, that is Electrical, Electronics and Telecommunication Engineering Section Committee of IESL, picked a very apt, very timely, almost hot topic of the day for the country to educate how to deliver stable power system to the consumers. And I'm glad to see that increasingly our engineers, learned engineers, are out there in the public, such as this memorial lecture, educating the public about this matter. Because it is time that the engineers come and speak to the public. So Professor Uday Annakage, I'm very happy that you are here to deliver this lecture. Thank you very much, sir. And congratulations to the sectional committee. With that, Engineer Labesegara, it's over to you. Let's enjoy the lecture. Ladies and gentlemen, it's a great time to enjoy this lecture. Thank you very much. Over to you, Engineer.
Thank you very much, Mr. President. And now let me have the honor of introducing our speaker today. Professor Uday Annakage is a professor of the Electrical and Computer Engineering Department of University of Manitoba, Canada. He has more than 30 years of experience in teaching, researching and consulting. He has supervised more than 20 PhD students and several MSc students at the University of Manitoba and University of Auckland, New Zealand. His main specialization is power system stability and security assessment. He received the BS Engineering degree from University of Morobro in Sri Lanka in 1982 and MSc and PhD degrees from the Institute of Science and Technology, University of Manchester, UK in 1984 and 1987, respectively. He has served for IEEE and CIGRE working groups. He was the editor of IEEE transactions on power systems from 2009 to 2012, the head of Electrical and Computer Engineering Department of University of Manitoba from 2008 January to 2012 December, and acting head from 2005 July to 2006 June, and 2020 July to 2021 June. Has published over 125 articles, including 60 articles in peer-reviewed journals. He was the convener of the IEEE Task Force on Dynamic system equivalents. The convener of the CIGRE working group on application of phasor measurement units for monitoring power system dynamic performance. And the technical committee program chair representing the Power System Dynamic Performance Committee of IEEE Power and Energy Society. Currently, he is the secretary to the CIGRE working group on guidelines for subsynchronous oscillation studies in power electronics dominated power systems, and the convener of joint CIGRE IEEE working group on evaluation of voltage stability assessment methodologies in transmission systems. Having said that, over to you, sir, to deliver the oration today.
Thank you very much. Can you hear me clearly?
Yes, sir, we can hear you well.
Thank you very much for that introduction. Good evening, President of IESL, President-elect of IESL, past presidents of IESL, CEO of IESL, Chairman of Sectional Committee of Electrical Engineering, members of the Council, family members of the late Professor R.H. Paul, ladies and gentlemen. I would like to thank IESL for giving me the opportunity to deliver this lecture in memory of Professor R.H. Paul. I have not met Professor Paul, but I knew him as a leader in electrical engineering education and a great mentor. During my undergraduate studies at the University of Moratuwa, my professor and also my mentor, Professor Sam Karunaratne, used to speak very highly of Professor R.H. Paul's contributions. That's how I know Professor Paul, and I have great respect for him. Again, I consider myself very fortunate to get this opportunity to deliver the memorial lecture of the father of electrical engineering education in Sri Lanka. My topic today, as mentioned a while ago, is secure operation of power systems for interruption-free supply to consumers. Let me share the screen. I hope you can see my screen.
Yes, we can see you.
Okay, thank you very much. So to give a quick outline of what I'm going to include in my speech today, I will start with steady state operation, what we mean by steady state operation of a power system. Then I'm going to move on to definitions of formal definitions of power system stability as published by IEEE and CGRE working groups and task forces. After that, I want to talk about the role of System Control Center. Then I want to talk about secure operation, what we mean by secure operation and how do you perform security analysis, what it involves. As essential parts of security analysis system in an energy management system, I'm going to touch on data acquisition and state estimation, but I'm not going to go into details of that. I'm going to briefly mention synchro phasor measurements and power system models. Finally, I want to talk about challenges. Security assessment is not an easy task. I'm going to talk about solutions and what it needs for a power system like Sri Lanka. Steady state operation, we often say steady state, but power system is never at steady state. This because loads change all the time. People switch on loads, switch off loads. In addition to that, there's a change of load during the day, and the generators or the governors, primary frequency control systems, try to track that load and adjust generation accordingly. So what we call steady state, we are going to see, we see small changes in voltages, system frequency fluctuating slightly around the nominal frequency of 50 Hertz for Sri Lanka. So it's really not steady state. Precisely speaking, it should be called quasi-steady state, almost steady state. So in my talk today, whenever I say steady state, what I mean is quasi-steady state. What do we expect at steady state? We expect voltages to be within acceptable limits, and for most utilities, and I believe it's true for Sri Lanka, acceptable limits are within plus or minus 5% of nominal voltages. And the other thing we expect is that the loading of transmission lines and all other components, transformers, all other components within the operating limits. I must also add that the frequency of the power system must be close to nominal frequency, and again, must be, for most cases, must be within plus or minus 1%. Now let's talk about power system stability. I want to touch on formal definitions of power system stability. So this chart on the slide is the most recent classification of power system stability. As you can see, I took this figure from the publication itself, published in July 2021, last year. It was the work done by a task force on classification of power system stability under IEEE Power System Dynamic Performance Committee. As you can see, there are 5 categories under power system stability. I want to focus on the 3 categories to the right of this chart. And these 3 have been the standard, most accepted types of power system stability for a long time. In 2004, IEEE and C-grade joint task force came up with this classification, which included the 3 categories to the right of this chart. And as I said last year, the new publication included 2 other categories, resonance stability and converter-driven stability, as new categories of power system stability. And the reason for that is most utilities around the world are seeing increasing levels of renewable energy integration into their grids. So along with this addition of renewable energy, and renewable energy is connected to the grid through converters, power electronics converters. So there are some new issues, engineering challenges, and of course, there are solutions. And the resonance stability, just very briefly, resonance stability is, any power system network or any electrical network can have resonance frequencies, especially when there are series compensated transmission lines, introducing capacitors, and the line inductance. So we have natural resonance frequencies in the network, and there's a tendency for converters to excite these frequencies and make system unstable. And the other thing that can happen with the introduction of converter integrated generation is the controllers of converter can interact with the network, and maybe in some cases nearby auxiliary controls of nearby dynamic devices. So those must be considered when you evaluate whether a system is stable or not. But today I'm going to focus only on rot angle stability, voltage stability, and frequency stability, because I think the Sri Lankan power system is not, as far as I know, Sri Lanka power system doesn't have significant integration of converter-based generation. Now, rot angle stability is further divided into transient and small disturbance. I'm going to talk a little bit on that later. Voltage stability, large disturbance and small disturbance, or short-term and long-term voltage stability, and frequency stability, again into two categories, short-term and long-term. Okay, now let's look at the formal definition of rot angle stability. Rot angle stability is often referred to as transient stability, but the classification recommends using the terminology rot angle stability instead of transient stability. So rot angle stability is concerned with the ability of the interconnected synchronous machines in a power system to remain in synchronism under normal operating conditions and to regain synchronism after being subjected to a small or large disturbance. So there are some key phrases in this definition. Remain in synchronism, normal operating conditions, and regain synchronism, small or large. So these are important the keywords in the definition, and one can elaborate this for hours and hours. I just included a trace of speed of a synchronous generator. This came from one of the simulations. And this is when a short circuit fault happened in the system and the fault was cleared. And then the synchronous generator, this particular generator, stabilized. We can see a few large swings in speed, and then the amplitude of these swings getting smaller and smaller in an exponential manner, and it settles at a new equilibrium. And if you pay attention, you can see that new equilibrium is not exactly the same as the original speed of the machine, slightly higher, but as long as it's within the limits and steady, it's considered stable. So there are two things here. In a synchronous generator, there's an electromagnetic torque, and the torque can be resolved into two components in quadrature. One is called synchronizing torque, and the other component is called damping torque. So initial swings of the machine to turn the machine back, or the speed increasing and to reach a peak and coming back, is because of the synchronizing torque, and the subsequent damping is due to damping torque. So for stability of a synchronous machine connected to a grid, one needs both synchronizing torque and damping torque. And damping torque is one of the big topics in stabilizing a power system. And this can be achieved by adding auxiliary controllers to the excitation system of the machine. Now, voltage stability. Voltage stability refers to the ability of power system to maintain steady voltages close to nominal value at all buses in the system after being subjected to disturbance. Again, the key phrases here are maintain steady voltages and subjected to after being subjected to a disturbance. And is mainly determined by the characteristics of the loads and the transmission system. We know in circuit theory, there's a maximum power transfer theorem that dictates that for a certain given circuit, there's a maximum theoretical power that it can transmit. And the same thing applies to the transmission network. For a given transmission network, there's a maximum power that it can deliver at a given node. And of course, your load connected to that node must be less than that maximum theoretical limit. Now, what can happen in a system is you can suddenly lose one component of the power of the network. Maybe you lose one transmission line, one transformer, or any component. That changes the topology of the system. And as a result, the maximum power transfer capability limit can decrease. And if your load is still below the new maximum, that's fine. If your load happens to be higher than the new maximum, of course, that load doesn't exist. What happens is the load will decrease almost instantaneously. And the voltage level will go down. But what happens with dynamic loads is, although the consumption decreases instantaneously or almost instantaneously when the contingency happens, dynamic loads will try to pick up the load to the previous levels. So in that process, it might drive the network into the maximum power transfer capability limit. And at that point, if you reach that point, then the next thing that can happen is the voltage collapse, voltage instability. And another factor for this maximum power transfer capability is the electrical distance between the load and the nearest point where the voltage can be controlled. To control the voltage, you need reactive power. So what's the nearest point where reactive power sources are available to control the voltage? That's a very important thing when it comes to voltage stability, because under highly stressed situations, if the reactive power supplying devices like static power compensators, STATCOMs, even synchronous generators with excitation control, if they reach the maximum limit, then the nearest voltage control point to the load will be moved to a further away point in the grid, increasing the electrical distance between the load and the voltage control point. That will decrease the maximum power transfer capability. So these things need to be considered when you evaluate a power system operation to see if it is voltage stable. The third type, frequency stability. The definition is frequency stability refers to the ability of a power system to maintain steady frequency following a severe system upset, resulting in significant imbalance between generation and load. And I added this for a small islanded power system. Frequency stability is more challenging than for a large power system, because large interconnected power systems support each other when a disturbance happens in one of the control areas. The trace shown on the slide is a typical response of frequency of the system to a disturbance. Here, the disturbance is some event creating a mismatch between generation and load. So we can see frequency is dropping. So mismatch is a generation deficiency situation, load higher than the generation. That can happen if we suddenly add a load, or the generating unit trips off, creating the imbalance between generation and the load. So the response of the system frequency has, as you can see, 3 overlapping periods. First period is the inertial response, then the primary frequency control response, that's the governor response, and the secondary frequency control response, that's the response of the automatic generation controllers, essentially giving integral feedback, or it could even be a system operator in a control room, system control center, adjusting the power generation set points of generators to bring the frequency back to the nominal frequency of 50 Hertz. Inertial response is a very important aspect. In a conventional power system with synchronous generators, only synchronous generators injecting energy. Inertial response is the response of the generators, natural response of the generators due to inertia of the rotating mass. Due to the inertia of the rotating mass, there's a huge amount of kinetic energy stored under normal operation. And when there's a disturbance, the natural response of the generator is to release this kinetic energy to supply to cater for the mismatch between generation and load. That results in a drop in frequency, but it's somewhat act like, well, it is stored energy. Although we say that there is no stored energy in the power system, there is in the form of kinetic energy of rotating machines. Now this is becoming more and more important nowadays, because when you connect converters, power electronic converters, there's no direct rotating kinetic energy directly behind those converters. So the sensitivity of system frequency to any generation load mismatch will be higher unless those converters are controlled to act like synchronous generators during an emergency, during a disturbance. So that's a very quick recap of 3 types of stability. Now, to assess whether a power system is secure, steady state alone is not enough. One has to consider what can happen in the system. For that, we have to prepare a list of contingencies, line outages, equipment outages, can be faults happening on the power system. And this list is prepared based on previous experience. So previous experience means there's statistical information going into that. That list can be, maybe 50 events that we are most concerned with. And these are the most likely events. And also one must consider the high impact events. Those are the events that are less likely to happen, but if it happens, the impact is going to be high. So with some engineering experience, operating experience, one has to come up with this list. It's called credible contingency, or list of credible contingencies. And that list is very specific to a given power system network. Now, System Control Center has the task of maintaining the security of the power system, continuity of supply to the consumers. The subtasks monitor the power system continuously, and information is received from the entire network, across the entire network, and then perform security assessment in a certain cycle. So here I'm taking 15 minutes as the example of cycle time, which is an acceptable security assessment cycle time by most utilities. Then you need energy management software to process that information, essentially to perform security analysis. The outcome of the security analysis is a set of alarms if there are, and the operators receive these warning alarms on the consoles in the control center with suggestions of preventive or corrective actions. Preventive actions is when everything is okay, the steady state is okay, but if any of the contingencies in the list of contingencies occur, then system is going to have some issues. So it's an early warning before that contingency happens. So the system control center, the control engineers can take preventive action. Sometimes preventive action may not be necessary, but you can arm your protection in case that happens and be ready. And the contingency may never happen. And that's better. So for secure operation of power system, just summarizing, one has to check whether the voltages are within acceptable limits, loads of all components within acceptable limits. So we are talking about the current operating condition. And if you are happy with that, then you have to check whether these conditions are satisfied under credible contingencies from the list of contingencies that I talked about. Then for each stability category, rotor angle stability, you have to check whether the rotor angle stability is maintained after disturbance from a credible list. You have to test the voltage stability. You have to test the frequency stability. For each test, there are different tools, different indices that you can look at, and also the models of the power system that you use in simulation to do this test vary depending on what type of stability that you are testing. For rotor angle stability, you need certain models. The details of the models can be different from rotor angle stability to voltage stability to frequency stability. So to put all this in one big picture, what do we need? We need to obtain most up-to-date power system states using SCADA and PMUs. PMUs are phase measurement units that use synchrophaser technology. And as far as I know, Sri Lankan grid has 2 synchrophaser measurement units, one at Biyagama and one at Kotmale, those substations. The difference between synchrophaser measurements and typical SCADA measurements, SCADA stands for supervisory control and data acquisition. The difference is the synchrophasers are synchronized. It doesn't matter whether you take the measurement at Anuradhapura power station or Anuradhapura substation or Kotmale substation. You take the measurements, sample the measurements, and add a timestamp from GPS and transmit it to the system control center. So when the system control center receives this data, they don't come in a synchronized manner because there are delays of transmission and calculations and so on. So one needs a program at the system control center to align this data according to the GPS timestamp. And once you align it, the information is very useful because you have captured what's happening. It's a very good snapshot of what's happening. Then you have to create the system model using the most up-to-date information because you get the circuit breaker status, whether the circuit breaker is closed or open, and all this information. You create the system model. You also need to forecast the load. And we are not talking about forecasting load for next month, next week, next year. We are talking about forecasting the load short time. And I already mentioned 15 minutes. So in that context, what I mean is forecast the load what's going to be the load in 15 minutes from now. Then for that forecasted load, perform power flow calculations for contingencies drawn from the list of credible contingencies. And if you're happy with that, then we do root angles stability, voltage stability, and frequency stability simulations for the contingencies drawn from the list of credible contingencies. In particular for voltage stability, sometimes we don't do the simulation, time domain simulation. We calculate indices to see how close we are to voltage collapse situation. Are we at a safe distance from that? So based on all these simulations and computations that's happening behind, the operator gets alarms if there are any warning signs. If not, nothing comes. And if there are alarms, operators take preventive or corrective actions to respond to this. So just to get a better picture of what I just explained, I put everything into a timeline. Let's say now the time is, let's say it's 6 a.m. now. We want to determine whether the power system is going to be secure at 6:15. 15 minutes from now, is the system is going to be operating in a secure manner. So I just put some times. At 6 o'clock, you obtain most up-to-date power system states using SCADA and synchrophasor measurements, PME measurements. Also, create the system model using the most up-to-date information and forecast the load. So at 6 a.m., we forecast the load for 6:15 a.m. In 15 minutes from now, what's going to be the load? So this is the load at various load centers. Then perform power flow calculations for contingencies drawn from the list of credible contingencies. So in my timeline, I'm seeing 6:02, but it won't take 2 minutes to do the other tasks. So start even early. Perform security analysis for contingencies drawn from list of credible contingencies, and allowing about 8 minutes for that. Then issue alarms if simulations of security analysis results in violations, and then between 6:11 to 6:15, operators take preventive actions. In preparing for the operation of the power system for the next 15-minute interval. And then at 6:15, you start the process again. So this is a near real-time monitoring and control of a power system. So what do we need? We need a reliable SCADA system complemented with synchrophasor measurements, and that information that we gather has a lot of redundant information, which is necessary to have redundant information. So you need state estimation software to come up with the current snapshot of the power system. We need models of all power system components and their parameters. That means transmission lines, transformers, generators, and all the auxiliary controllers behind the generators. And the list goes on, SVCs, STATCOMs, you have. And you need a list of credible contingencies based on historical data, and to that list include highly probable as well as high impact events. You need software for fast computing of power flow, root angle stability, voltage stability, and frequency stability. And these tasks can be done in parallel because you can do power flow calculation quite independent of root angle stability assessment and voltage assessment and frequency stability assessment. So they can be running on 4 different computers, and or even more, because you repeat this for different contingencies. And one needs an energy management system that combines all of these tasks. So can we do this in Sri Lanka? Sri Lankan power system is a small power system compared to large interconnected power systems. And I'm confident that the present day computing power is adequate to do this. But it's very important to have accurate models of the components of the power system. That must be the starting point. And this is useful not only for operation of the power system. We are talking about operation. Security assessment is power system operation, but for planning, planning studies, or even when there's a big event, blackout or brownout, if you want to do a study and see what really happened, you need accurate models of the components of the power system. I hope I'm doing okay with time. According to my watch, I have taken about 35 minutes so far. Please let me know if I'm going over time. Now, can we do this for a large system? That's the challenge. Large power systems in North America and Europe have several thousand nodes and several thousand dynamic devices, generators, and so on. So because of that, it requires a massive computing power to complete all computations that I discussed within an acceptable time period. I keep on bringing this 15 minutes as an example. So all these calculations I talked about needs to be done in 15-minute cycles. Some utilities use dynamic reduction to simplify the power system. The Manitoba hydropower system, that's the utility in my province, is connected to the US network to the south, Ontario network to the east, and the Saskatchewan network to the west. So it's a huge network, huge power system. So Manitoba Hydro uses system equivalents to represent the external system. That's the external meaning US network, Ontario and Saskatchewan network, represented by an equivalent. Otherwise, you can't carry out this security assessment. Well, I should qualify that. With the current computing power, you can't do it without dynamic reduction. And some utilities use artificial intelligence techniques, that is machine learning, to speed up the process. Again, going back to the utility that I'm more familiar with, Manitoba Hydro, they use some machine learning methods. I don't want to name the exact learning methods, but they do. And my research group, well, Power Systems Research Group at the University of Manitoba, proposed some artificial intelligence approaches to speed up the process. And I'm going to spend a little time on briefly going the fundamental concepts behind the methods that we proposed. Before that, how can machine learning help? What does it do? Essentially, it learns the steady state and dynamic behavior of the power system using simulations and produce an intelligent function to predict potential system instabilities. So we're talking about doing a lot of simulations, time domain simulations and calculation of indices in every 15-minute cycles. And that's a huge computing task. But if we can create an intelligent function that takes in only the current state of the power system and simply say stable or unstable. And to do that, you have to train it. So learning, we have to make learning near real time, because you can never come up with this intelligent function that will be valid any time of the day, as you know, the grid is a very dynamic thing. The components of the transmission system, generation system can change, loads change, load patterns change. So it's an almost impossible task to come up with intelligent function that's valid for any system. I mean, any operating point for any contingency. So you have to do this learning in a near real-time basis. That's what we proposed. So to apply machine learning, you have to define the state of the power system using nodal voltages and magnitudes, nodal voltage magnitudes and phase angles. We know any electric circuit can be uniquely defined by voltage magnitudes and phase angles of all the nodes. So that's a unique representation of the state. Then generate a large number of power system states. Now these are not the state that the power system is currently in at this point in time, but computer can generate large number of operating points around where we are, and then simulate contingencies for each power system state and label them as stable or unstable. So we have, on one side, we have the state of the power system, and we have mapped whether the system is stable or unstable for different contingencies. And that information, if we use that information to train a machine learning algorithm, this is the task number 4 in my slide, to take power system states as input and classify it as stable or unstable. Then when it comes to near real time, you don't perform these calculations, you simply input the state that you measured. So those are called unseen states. The machine learning algorithm has never seen that before, but it has seen a lot of simulated states, enough simulated states to predict the stability state for this unseen state without having to do time-consuming simulation. So that's how the machine learning can help security assessment. Just to give an example of instability. So here we see a simulation where a fault, short circuit fault, has occurred, and we are plotting the voltage magnitude at different nodes, different buses of the system. So you can see when the fault occurred, the short circuit fault occurred, voltages dipped to a very low value, depending on how close you are to the fault, how much dip you experience change, as you can see. And then the fault is cleared and the voltages, at least temporarily, recover to original values, so almost close to the original values. But in this example, it cannot hold these voltages for long. It starts sliding down, and then towards the end, you can see some oscillations and system going unstable. Rotor angles and generator speeds also shown in this figure. So this is a unstable situation, transient instability or rotor angle instability. So you can see, if you want to determine whether the system is going to be stable or not for rotor angle stability, you have to do a simulation. Typically, it's recommended that we do the simulation for 5 seconds, 5-second simulation window. So to go through some of the ideas proposed and tested by Manitoba University of Manitoba Power System Research Group. I'm just going to just pick three of those. One of my PhD students, Bharti Jayasekara, came up with this method of derivation of an accurate polynomial representation of the transit stability boundary. And Francisco Gomez, PhD student from Venezuela, under the supervision of my colleague, Dr. Atula Rajapaksha, came up with support vector machine-based algorithm. We learned a lot of new things through this project. And then my PhD student, Janak Giganage, we did a collaborative project with Manitoba Hydro. Tony Weeks and Brian Archer were our collaborators. We came up with some very interesting way to speed up this security assessment. I'm not going to present those methods, but just capture some key concepts. In the first paper that I showed in my slide, let's say we have this is a two-dimensional real power system state has very large dimension. You can't show it pictorially. So we have two-dimensional example here. It's an ellipse. Let's say a system is stable inside the ellipse, unstable outside the ellipse. So the boundary is non-linear in terms of x1 and x2. But if you convert the variables to x1 squared as one variable and x2 squared as other state, then the same region, that non-linear elliptical boundary becomes a straight line. So with the variable transformation, we can make the classification of stability much easier. So that's what we did, and the machine learning technique we used was kernel ridge regression. And with the Francisco Gomez's PhD, supervised by my colleague, Dr. Atula Rajapaksha, something very interesting was instead of looking at the root angles, we naturally tend to think that root angle is the most, has the closest affinity to transient root angle instability. Well, they found that the voltage recovery, how fast the voltage recovers, has a lot of information about what's going to happen in what's going to happen subsequently. So what they did, they captured the voltage recovery trace and sampled, took few samples of that voltage recovery and used that pattern, fed that pattern to the machine learning algorithm to learn to predict what's going to happen in the future in the sense in few seconds from here. So if we have this, then the transient simulation that we have to run many times in the security assessment cycle, we don't have to do the simulation for a long period. Offline, we do the simulation and train the method, and the train method needs only few samples of the voltage recovery. So that was a big eye-opener for us, and this paper has received a large number of citations. And then with that idea, my next student, Janak Giganage, came up with another interesting idea. Root angle stability depends on, okay, let me backtrack. When there's a short circuit fault, what happens is synchronous generators accelerate and speed up, accumulating kinetic energy. Once you clear the fault, if the machines can get rid of that acquired kinetic energy, feed that extra kinetic energy back to the network, then the machine becomes stable. So that's another way of looking at the stability of the machine. And in back in 1970s, a lot of research work was published on using Lyapunov second method of stability analysis. And when it was applied to power grid, power systems, the Lyapunov function was referred to as energy function because it's the energy. So if we look at the energy acquired by a rotating synchronous machine during a fault and during the fault recovery, the mathematical expression, you take a careful look, it has different components. First part is the kinetic energy. Second and third components also, well, second and third components are potential energy. And the fourth component is the third potential energy component. It involves integration. And the main reason why people abandoned this approach was it's so time consuming because it involves integrating along a surface. So the idea that my student came up with was, now if we are using machine learning, we don't have to give all the information. Typically what we do is we give the voltages and phase angles and ask the machine learning algorithm to learn it. But if you bring it closer, help the machine learning algorithm by giving more physically meaningful inputs, it should be faster. So that's the hypothesis. So, that last component is the time-consuming component to calculate. So why not we calculate almost instantaneously? Calculate kinetic energy component and potential energy 1 and potential energy 2 components and feed that as inputs to the learning algorithm. And we did that, the hypothesis was right. We were able to train a support vector machine learning algorithm we use for support vector machine. We were able to train it to come up with this machine learning algorithm, train machine learning algorithm in a short time. So with that confidence, we wanted to prove that it works. So what we did, we simulated the IEEE 39-bus system on a real-time digital simulator. So it's like the power system. And we ran two processes, process A and process B. Process A to come up with the machine learning network, the learning part, and the train network is passed on to process B, another computer. Everything was connected to the local area network. So we took a snapshot of our system every 15 minutes to train the classifier. And then the process A learns about the system and come up with the classifier and pass that classifier on to process B. And the process B uses this classifier to assess security state of the power system. And every 15 minutes, process A receives a new snapshot of the power system and does all the calculations and pass it on. So process B continuously get revised, if you like, the intelligent function. And it also takes snapshot of the power system. But what we did was every 2 minutes, we repeated that. So, simply plugging in the information and checking the state is very fast. So we did that every 2 minutes within the 15-minute security assessment cycle. So this is process B that I referred to, simulated power system modeling real-time simulator, and we capture all the meters and convert to snapshots, compute input features. Those are the kinetic energy and potential energy terms. And then use the classifier provided by process A to simply say whether the system is stable or not, whether the system is secure or not. To summarize, so second part of my talk was on how to apply security assessment to very large power systems. But coming back to summarize, security assessment is a very important function for maintaining the continuity of electricity to the consumers. And I believe Sri Lankan power system is a small system. Computing power presently available is more than adequate to perform security assessment. But one needs validated models of the components of the power system. And also we need the energy management system that can perform all the functions that mentioned in one of my previous slides. So I hope I didn't take longer than the time allocated to me. Thank you very much for your attention. Happy to answer any questions if there is time.
Thank you very much, sir, for the valuable information shared among us. To be a definite assistance and guidance for local engineers, especially for electrical engineers. A memorial oration, basically, we do not have a Q&A session. If there are any clarifications to be made, our listeners may be able to send them to us, and we will direct it to you so that your response can be sent back to the respective parties. Having said that, wind up the session, let me invite Engineer Kosala Kamradeniya, the Chairman, Electrical, Electronic and Telecommunication Engineering Sectional Committee, to deliver the vote of thanks. Over to you, sir.
Thank you, Neil. Good evening to all of you. The President, the Institution of Engineers of Sri Lanka, President-elect, immediate past President, past Presidents, Vice Presidents, Executive Secretary, guest speaker, Professor Uday Annakage, council members and members of IESL, family members of Professor R.H. Paul, members of the Electronics and Telecommunications Sectional Committee, and ladies and gentlemen. First and foremost, on behalf of the Institution of Engineers Sri Lanka, I would like to thank Engineer Professor Uday Annakage, Professor in Electrical and Computer Engineering of University of Manitoba, for accepting our invitation to deliver this prestigious lecture, which is one of our most important annual events in the IESL calendar, in spite of your busy schedules. And also, Professor, we thank you for selecting a very timely and appropriate topic for our country for this memorial lecture. Moreover, we are indeed thankful to you for educating us, enlightening us with importance and techniques of maintaining an interruption-free power supply to the customers. Also, we appreciate and are so grateful to the family members of late Professor R.H. Paul, especially the two daughters of Professor R.H. Paul, Miss Sonia Kaspers and Miss Keith Paul, and the two sons of Professor Paul, Mr. Beverly Paul and Mr. Krisnik Dicker, and also Mrs. Neha Appature, niece, and her spouse, Mr. Eddie Appature, for participating in this event today. Also, on behalf of the Electronics and Telecommunications Sectional Committee, I would like to thank President Engineer Arjuna Manamperi, the President-elect Dr. Kamal Laksiri, and Executive Secretary Engineer Neela Besekara, and also the Secretariat for all the support given in making this event a success. A special thanks should go to Engineer Sandima Samarasinghe, who led and coordinated this event, and also to other colleagues in the sectional committee for their contribution in organizing this event. Last but not least, let me thank the President, President-elect, past presidents, vice presidents, council members, invitees, and every one of you for taking your time to be with us to participate in this event. This is Professor R.H. Paul Memorial Oration. Thank you very much. Wish you a pleasant evening.
Thank you very much, Mr. Chairman. Now, shall we call it a day then? In the meantime, if there are any queries on this thing, you can send your questions to es@isl.lk. I have typed it in the chat box. So we'll forward it to Professor Annakage and send you his responses. Thank you very much for participation. Thank you very much, Professor Annakage, and President, and everyone. Wish you a good day.
Thank you again for the opportunity given to me to deliver this very prestigious memorial oration.